essentially the probability function, right, takes elements of or members of this collection F to the real line or the piece of the real line 0 1. It is a closed interval in the sense that you can get both 0 and 1. In fact, we get both these endpoints, right. P omega is in fact exactly equal to 1, and that is a universal convention that we follow, right. Everybody uses it worldwide, has been using it for the last 50 ever since this formalism was put in place, right. And of course, the null set has 0 probability, which is also very intuitive, because the null set corresponds to the impossible event, right. You want it to have 0 probability anyhow. Then the most important thing beyond this is this statement here, right. If you take any two subsets A or sets A and B which are mutually exclusive, then the probability of the union of A and B must be the sum of PA plus PB. So these are all the rules or axioms that we use, right, to construct this probability function, right. So, so if you have any doubt about what an axiom is, you can think of it as a rule, right, you do not question it basically, right. So this pairwise additivity axiom, right, obviously extends to any collection of a finite collection of mutually exclusive subsets. Note that, right, if A, B and C are mutually exclusive, then pairwise also they are mutually exclusive, right. So you can have more than two mutually exclusive subsets in a sub collection, right. So extends to axiom number 3, mutually exclusive collection AI, I equal to sum 1 to n, let us say, right. This union, right, is also obviously defined, and it is a set in F, because we have said that at least in F, right, unions have to be members of F, right. So there is so obviously we have to assign a probability to the union of any collection of sets which are in F. So this the assumption automatically is that all AIs are in F. Again, for the discrete case, all these questions of what is F does not arise, because we are always going to take F to be every possible collection of every possible subset we can form out of omega, right. So, so anyway, so all of these things, statements are going to be true for all omega Fp, right, regardless of whether F is a power set or not, okay, which is why this is just an example in a way, right, it is a special case, whereas all of this applies to everything, or any probability triplet that you define, right. So for any this pairwise additivity clearly extends to any collection of n mutually exclusive subsets because of induction, right. If A, B and C, you start with A, B and C, which are all three exclusive of each other in the sense only one can happen at any one time, right, then A union B will be exclusive of C, and so on and so forth, right. So obviously this extends quite obviously. What does not follow from this finite additivity axiom is the infinite additivity, which has to be also added as an extra thing, and that the infinite additivity axiom is needed when you go to spaces which have infinite number of elements, right, whether countable or uncountable, right. Now the so called infinite additivity, this is an extra, this is an extra. So if this AI 1 to infinity is, right, a collection of mutually exclusive events, then So this is stated on top of this, right. Note that this again is a number which has to lie between 0 and 1, right, and this union has to be no bigger than omega, okay. So so the infinity really does not really cause any problems at all, right. And obviously you will run into this kind of situation when your omega is big enough to support, right, an infinite collection of subsets, right, whether countable or uncountable. So anyway, so with these axioms, right, we can now proceed with the development of the theory, right. What are the properties, other properties that we can derive from them, and so on and so forth, right. So so we should take a little bit of a pause to understand this and appreciate this and let it sink into our heads, right, that these building blocks are in fact sufficient pretty much to build up the entire theory, right. It is a very profound in a sense situation, right, that a very small number of rules is all that we need to keep in mind. We need to keep in mind how we form omega and then the f, and then apply this the p to all the elements of f, and then follow these axioms to build up the theory, right. Okay. Now before I move on to the actual the probabilities, the properties of the probability measure p, right, let us take up the the assignment of probabilities to elements in f for the case that f is countable, or sorry, when omega is countable, right, or discrete. When omega is discrete, i.e. omega equal to capital Omega is omega 1, omega 2, omega 3 and so on dot dot without, right, can go on forever if need be, right. Then right, how do you go about assigning p so that all these axioms are satisfied, right. Basically you start with a bunch of numbers pi, right. What are these numbers pi? Then we assign a number pi to the probability of this singleton set omega I. Some number pi, right. What does this notation mean? It is the singleton set, right, which consists only of the outcome omega I, right. So obviously a singleton set which consists only of omega I is exclusive of any other singleton set which consists of different outcome, right. So note there is a subtle difference between writing just this outcome omega I and writing it as a singleton set, right, although in engineering terms there may not be any difference, but in mathematical terms there is a difference, right. This is a singleton set, this is just an outcome, right. Anyway, but you can think of pi as just the probability assigned to omega I, right. So we assign this pi to this singleton set omega I such that what rules are we going to follow? Let me go back up there and write this, right. How are we going to assign these PIs? Let me say pi equal, right, such that this pi is between 0 and 1 for all I, obviously, right. This obviously has to be satisfied, otherwise pi cannot be a probability, right. Then secondly, sum of pi I equal to 1 to infinity is 1. So when omega is discrete, all of this applies only to this case when omega is discrete, right? It is very difficult to do probability assignment consistently if you start with all the subsets to which, or all the sets in F to which you want to assign probabilities, right. It is much easier, and this is what we have always been doing in all our earlier, right, encounters with this subject. We have done it implicitly without, right, putting a formal statement on it. Now it is time to look at it a little more formally. All that we have done up to now, right, when omega is discrete, is assign probabilities to the singleton subsets such that the probabilities add up to 1, the probabilities are between 0 and 1 themselves. So these two things, right, the statements are sufficient once again to generate the probability of any event which is going to consist of more than one of the elementary outcomes, right, of the outcomes of capital omega. How? Because the simple additivity rule, right, then gives you this. Supposing you want PA, some collection of omega I such that, right, this is a circular definition, right, but anyway, does not matter, I am not being very rigorous in mathematical terms, but it is okay, let me just write it in some notation like this. This colon stands for such that, right. So obviously it is it is obviously a circular definition, but does not matter, let it be, right. So you since I do not want to tie down my A to be an example of omega 1, omega 2 or whatever, right, some collection of points omega I is in A. So what will be PA then? What is PA in terms of PI? I have put a summation, right, I add all the PI's, but obviously I do not add all the I's from 1 to infinity, I add only those I's such that what, omega I belongs to A. So this has to be written mathematically like this, I such that omega I belongs to A. So you apply this simple principle to any set A or any event A, right. So this itself is consistent with the axioms, right. After all, what is A? A is the union of all the elementary events, right, of corresponding to the omega i's that belong to A, right, and that has to be obtained as an addition according to the axioms we have just written down. So therefore that addition is here. PA is obviously between 0 and 1, can never be below 0, can be, we are adding non-negative quantities, so the result can never be negative, the result can never exceed 1, because if you put all the PI's together you get unity. So clearly it is between 0 and 1, right, and if you take any two sets A and B, A union B, right, will consist of a larger collection of points, right, a larger collection of outcomes, and definitely the probability of A union B is going to be the summation of PA plus PB. I think it is obvious from this construction. I do not think I need to spend more time on that than this, right. Just keep adding, that is all, right. A union corresponds to addition when sets are, or when the events are exclusive, right. So this is a very intuitive way of of assigning the probabilities which we start doing, right, when we start studying the subject, right. Note that we are not putting any, right, the theory does not say how we should come up with these numbers Pi, especially when the number of points is large, right, the number of outcomes is large, or right, or even countably infinite, right. It does not say how we should choose the Pi's. So then the PI's must reflect reality in some sense, right, otherwise the calculations we do with the PI's are not going to mean much at all. So how do we make sure these, how do we get some correspondence to the real world? Through this concept of relative frequency, right. If we run the experiment a large number of times, right, and then count, right, let us say we run the experiment some capital N times. I have used small n out here, so I have to use a different n. Okay, so so since n is out there, small n, let me so what is the real world connection? What is Ni? Ni omega I. So probabilities are always, right, associated with relative frequencies in application, right, but that is the application of the theory, right. So the theory comes in between the observation and the application. You observe something, then you build a probability model, you compute using the probability model, then you have some other numbers that you have to take back to the real world, right. So the theory itself is divorced from both the observation finding and the application. It completely exists in almost like independent of the real world, right, except that it has to follow the axioms. But for the theory to give you useful numbers at the output, right, the input has to be meaningful. The input is meaningful only if, in this discrete case, if the PI's, right, are roughly, right, correspond to this Ni. I am not putting, note that I am not putting equal to, because this Ni by n is a very fuzzy quantity, right. There is no fixed value. For different n's you may get different Ni's, or you will get different Ni's, but you may get different Ni by n, isn't it? The ratio Ni by n need not be the same for any collection of n trials, right, any set of any super experiment where you, right, do the experiment n times. So since this can vary, but it is observed, right, experimentally that, right, for many experiments which are repeatable, that the Ni by n does in fact, right, converge to some number which is reasonably, right, the same. So you have to do some juggling of the observations you get to fit into a probability model. So in this class, in this course, we are not concerned with that problem at all, right. What is a good probability model to use for a particular experiment, we are not going to worry. It is completely beyond the scope of this course, right. That is in fact a much harder problem than, right, it is an empirical problem. Here we are only building the tools of the theory, which are, right, occasionally we use, look at applications, but certainly we are not going to go out and collect data and try to fit probability models. That is, as I said, it is not an easy thing to do, and, right, it is more in some cases an art, not really a science, right. Anyway, so in some other cases this Pi can be assigned using some symmetry arguments, right. If you have a fair coin and you can only get head or tails out of it, and you say the omega is just head tail, right, there is no reason to say that probability of head should be much different from the probability of a tail. So the standard thing to do is say yes, they both, right, have half-half. Okay, that is very trivial. What about the next most commonly cited example of a die, a 6-face die? Again, the 1/6 probability associated with each face of the die is just a statement that you do not expect any one face to occur more than any other face. All of them are equally likely. So this, so if unfortunately did okay this I did not, okay, let me use a different notation for let us say omega. Supposing omega has, this is all by the way only for discrete spaces, right, we are only looking at discrete spaces now, right. So, supposing let us say k elements, this capital omega is basically omega k from, or omega I will keep this as I and omega to k, right. This is just one particular, is what do we call this? This is equally likely assignment, right. If you set this pi equal to 1 by k for the, right, k is at omega, capital omega is exactly k elements. This is the, so very popularly, right, thought of as the only, earlier they used to think this is the only way that you could do it, but that now we know that's obviously not necessary, right. 200 years back, when gambling houses, when they started to apply rudimentary probability, they had this right idea that all basic, the outcome, the elementary outcomes must all be equally likely, and then of course you could get different PAs by adding different numbers of outcomes, right. But essentially they started off with this, right. This is a so called classical theory which was prevalent long back, before the axiomatic treatment took over, right. So this is just one special case, right, but it need not be always like this. You could, right, have, even in the case of equally k finite number of outcomes, you can have unequal, you start off with an unequal probability distribution. There is no, the theory does not preclude that at all, right. Okay. So this anyway, so having said this, right, now I think we can move on to the general situation, right. Omega, go back to the omega FP, the general case, right, which applies in all probability problems, or and look at the probabilities, the properties of the probability measure.